So let us begin with module 5. Very initially in module 1, we had discussed there will be how many approaches that we will be studying? How many? Number? Four. नाम बताओ. Greedy, dynamic, divide and conquer, backtracking, and branch and bound. There are 5. Okay. So today what we are starting to do is something based on a graph or a tree, and the tree, whenever we see that there is a root, then we have 2 child nodes, and in the next level again there are 2 child nodes, and so on. If we go on moving down the tree grows exponentially, right? So आज के जो algorithms है, they will take exponential time. We are trying to reduce down the time a bit by pruning, but still the time remains exponential. So the first technique that we have is backtracking. So backtracking is, as I mentioned, wherever the number of choices will grow exponentially with the problem size, we will use there. Again, we'll be having a set of constraints, we'll be having an objective function. Again, the solution will optimize the objective function, and the solution has to be feasible. So there are some terminologies with respect to backtracking and branch and bound. At the root, we'll have no choice. At the next level, we have the first choice. At the next level, we have the second choice, and so on. Then we have to return a path from the root to a leaf, which will be the candidate solution or feasible solution or optimal solution. There are nodes which are termed as non-promising. There are nodes which are termed as promising. Non-promising nodes are a node which cannot lead to a feasible solution, and promising nodes means wherever we get a feasible solution at that particular leaf node. I hope people remember DFS and BFS. So here in backtracking, we are following DFS manner. That is, root node ka child node will be generated. We expand or explore that child node, move further till we get a solution. If we do not, then we backtrack to the fail. So that is from that. This is from where the backtracking term comes. So there might be problems wherein I have to check all the possibilities. That is why the state space search becomes exponential. And we will be using backtracking if we do not find a solution. So in order to find a solution, we will backtrack the path. There are a set of constraints that the problem should follow. These are termed as explicit and implicit. Please understand the difference. Explicit matlab xi की values जो final resulting tuple होगा xi उसकी values किस range में लाएंगे. And implicit means that how are these xi values related to each other. So we'll see, understand this by examples that we have to study in detail. अभी के लिए क्या याद रखना है? Final solution is a tuple. In that tuple, there are xi values. वो values किस range में रहेंगी? That is your explicit constraint. And how these values are related to each other? That is your implicit constraint. And there are 3 differentiators that make us understand हम किस तरह की problem को solve करें. So if I have only to find a feasible solution, मतलब कि ये जैसे let us say for a knapsack, ये item pick करना है कि नहीं pick करना है, that was a decision. So that is a decision problem. If I have to optimally fill the knapsack, that is an optimization problem. If I have to list all the feasible solutions, all the possible combinations which can be put into the knapsack to fill it, these are enumerating all the possible solutions. So depending on the question, we'll try to solve the problem in the manner it is being asked, as a decision problem, an optimization problem, or an enumeration problem. So how is the process of backtracking happening? There is a problem state. Each node is a problem state because I do not know where my solution is. State spaces, all the possible paths from the root to every other node. Solution spaces, the possible path from root to the solution node, right? Answer state is this node which will satisfy the constraint. That is why we are putting constraints that should be satisfied. Then there is a terminology as live node. Live node मतलब जो node generate हो गई है and all its children have not been generated. So it is in the process of exploration. E node is the expanding node. Currently जो node explore हो रही है, that is E node. Dead node is a node which is generated, which is not further to be expanded. Because we are saying कि हम nodes search space tree को prune कर देते हैं. Pruning का मतलब हुआ एक particular node पे we decide based on the constraints I cannot further expand it. That is why I declared that node as a dead node. So there are two ways to generate problem states, as I mentioned. If you remember your BFS manner and your DFS manner. So DFS is implemented using stack and BFS using queue, right? We all know this from before. We are keeping all the live nodes in these data structures. The differentiating factor between branch and bound and backtracking is this only. Branch and bound uses BFS and backtracking uses DFS. So DFS is stack of live nodes. I have a new child node C of the current E node R. Then this child node becomes the E node. DFS ऐसे चल रहा है. Then R will become the new node again. कभी जब subtree पूरा explore हो गया तो I'll reach again to the parent. Right? So this is DFS. BFS is there is a queue of live nodes. Wherein E node will remain the E node until it is dead. So when it is dead, when all its child nodes have been explored, child nodes have been explored and so on. So E node remains the live node. Here we are using the concept of bounding functions, which will be used to kill the live nodes. Otherwise, the tree will be very huge. So I'll require this tree again to be pruned. In that case, I need not generate all the child nodes. And at the end, we'll get a single answer, or we can also get multiple answers. That depends on your implementation. DFS may be multiple solutions आ सकते हैं if you are calling the function again, and DFS definitely gives you all the possible solutions. Whenever we are following DFS, it is termed as backtracking, and whenever we are following BFS, it's termed as branching. यहाँ तक समझा सकते हैं? These were the basic concepts, initial concepts or foundation concepts of backtracking and branching. Online students, is this clear?
Yes, miss.
Yes, ma'am. Yes, ma'am.
Now we have to move to a stage wherein I need to learn how to prune the tree so that the tree does not grow exponentially, right? So search pruning will help us reduce the search space and to get the solution faster. We will try to avoid those paths that will not lead to a solution. We will find contradictions using our constraints. So whenever there is a contradiction, I'll prune that particular thing. So let us understand how the new strategies are different from what we have studied earlier. So greedy में क्या था? We were not revising previously generated solutions. Here we are coming back to the previously generated solution in the form of backtracking. In greedy state space tree का concept नहीं था. यहाँ पे this concept is there. Greedy was less efficient. This is more efficient. And the examples, example problems wherein these approaches are being applied. These are the applications wherein we'll be studying to apply backtracking. The one in red is not in the syllabus currently. 8 quiz problem, sum of subset problem, and graph connector. Any one of you have any idea of these problems? Define कर सकते हैं? Yes. And what is the condition that a queen can attack each other? Anyone online?
Ma'am, it should not come in the same row, same column, and same like diagonal.
Okay. Now moving ahead. Same diagonal का मतलब not only this, you have to check both the diagonals. Any one of you, in terms of implementation, can tell me how will you check for the for both the diagonals? I want the condition in terms of I and J, how we are checking for both the diagonals. आया किसी को? क्या कंडीशन होगी so that this and this are not there? I is equal to, please बोलो who is speaking. I should not be equal to j. What will be the condition for these two? वो तो फिर 3/3 में और भी हो सकता है. I not equal to j is not the correct answer. There has to be a relationship between I and j. तो simple सी logic है.
Ma'am, if a queen is in I and J position, then the condition should be I plus 1 and J plus 1. Like it should not be equal to I plus 1 or J plus 1.
That you are telling for the primary diagonal. I am asking for the secondary diagonal. जो next 3/3 का मैट्रिक्स बनाया है, I am asking for that. And 2/2 में जो क्रॉस है, I am asking for that. हाँ? Be loud. If I is equal to length of matrix minus 1, उससे कैसे चेक करें? वही तो बोल रहा था. Can we add the row and column value? Okay, so will that be followed in 4x4 as well? What he answers is sum of I plus j should not be equal to n plus 1. Right? That is the condition that we are checking. And here what is happening in the main diagonal? I equal to j आ रहा है या I minus j की वैल्यू 0 आ रही है. तो you can pick ij, you can pick k and l. So I minus j equal to k minus l अगर है, that means they are on the same diagonal. So why were we discussing this thing? Because these offline people answered 8 queens problem is when we are placing queens on a 8x8 chessboard and the queens are in non-attacking position. Queens attack when they are in the same row, same column, same type. So that we'll see in detail when we are seeing this problem. Let us talk about the second problem. Sum of subset, any one of you heard of? सब पढ़ के बैठे थे. Given okay, so sum of subset problem is we are given a set has n items, each item is a value. We have to pick a subset जैसा problem बोल रहा है, and the sum of this subset should be equal to the given value. There is a set given of elements and there is a value given. तो हमें ऐसे subsets pick करनी है, that might be multiple solutions in this case as well. Moving to the third problem, graph coloring. Anyone online? Graph coloring problem? बोलो आशुतोष. Again, graph coloring problem can be related to map coloring problem. That is, we have a map wherein there are neighboring cities और हम क्या बोलते हैं जिनकी भी boundary common हो, they should not have the same color. So we try to replicate this into a graph and say that vertices adjacent to each other should not have the same color, and we have to try to color this map or the graph using minimum number of colors. Okay, so we'll see these in one by one. So this is the first problem that we have discussed. This is a 8x8 chessboard, and we have to place 8 queens. We can reduce this problem down to 4 queens problem as well for understanding purpose. A queen can attack if it exists in the same row, column, or diagonal. This problem can be solved by one placing the queens on the chessboard and checking for the condition. तो यहाँ पे कोई बता सकता है बैक ट्रैकिंग का यूज कहाँ पे आएगा? Or how are we saying that this problem can be solved using backtracking? Or how would be the tree formation for this problem? बोल रहे ना backtracking के लिए tree बनाना पड़ेगा. Okay, so how are we going ahead is मेरे पास root है और root में I am making a decision कि पहली queen को place करना है. For the first queen, how many possibilities do I have? 8. Without any constraints, I am a layman. I do not know when queens attack each other. So second queen के लिए how many possibilities are there? Again 8. Right? I don't have any constraints. Same row, same column, same diagonal constraints भी मेरे पास नहीं. Similarly for all other queens. So how many such possibilities we are encountering? If for every queen I have 8 combinations, so total leaf पे कितनी nodes आएंगे at the last level? 8 to the power 8. So this huge search space tree का size है. We have to reduce it down using the constraints. The solution is a vector of length 8, wherein I need to know that x1 अगर represent कर रहा है first queen को, the first queen की position क्या है, which column it is lying. So that is why it is a tuple of 8 values. We build this solution partially element by element, and ऐसा possible है कि एक element को place करने के लिए there are no possibilities left. At that point, I'll have to backtrack and change the positioning of the previous queen. Okay. So this is what we are doing is we are trying to put a queen into a row, and this is recursive. Again, we are trying to put the queen into the next row and so on. For putting the queen, I have to check for possible position in the column. If the position is available, we are placing it. If it is not available, then backtracking will be required, which is not mentioned here. For that, we'll check out the exact backtracking algorithm. ये तो problem बता रहा था manually हम कैसे queen को place करते हैं. This is what we saw, that there are 8 to the power 8 possibilities, and that is why we will move towards search pruning. So for search pruning, we will require constraints, right? मैंने starting में क्या बोला था कि explicit constraints क्या होगी? They will define what? The range from where xi can take the values. ठीक है? तो यहाँ पर 8 queens है, तो xi की possible values are lying in the range 1 to 8. Implicit constraints क्या बोला था मैंने?
Comparison between the pairs.
Comparison between the pair, or how are you relating two queens together?
Yes, ma'am. Relating the two.
Right. So यहाँ पे क्या relationship आएगी दो queens के बीच में? They should not be in attacking position, the same row, same column, same diagonal. That you have to check through the algorithm. How is this reducing the search space from 8 to the power 8 to 8 for factorial? Anyone? तो हमने जब constraint डाल दिया है, we are assuming कि one queen will be placed in one row. वो constraint हो गया. Column के लिए क्या हुआ? If I am placing a queen in one column, so for first queen I have 8 possibilities. For second queen, I cannot place in that particular column जहाँ first queen को place किया है, only 7 possibilities. For third queen I have only 6 possibilities, and so on. So the search space reduces down from 8 to the power 8 to 8 factor. So this is my tree. Abhi pruning has not been done. We are studying it for 4 queens to fit it into the slide. So please understand the tree that is over here. जब भी tree बनाएंगे, every level पे we are considering the next item or the next element. So over here the item or the element is queen. The first level means placing of first queen. I can place the first queen at first cell, second cell, third cell, or fourth cell. That is why I have 4 possibilities initially. After placing the first queen in the first cell, second queen can be placed in. We are right now only considering same row and same column. Same row का constraint कैसे हटाया है? We are explicitly assuming every queen is placed on a new row. वो constraint हट गया same row का. Column का constraint कैसे use कर रहे हैं? Using this same column में नहीं place कर रहे हैं. So what happens is अगर first queen को first column में place किया है, तो second queen के लिए I have left with only 3 options. Third queen के लिए I have left with only 2 options. And fourth queen के लिए I have left with only 1 option. That is why you can see the numbering is 1, उसके बाद 2, 3, 4 बचता है. 2 पे अगर place किया तो only 3, 4 is the option. 3 पे place किया तो 4 is the option. 4 पे place किया 3 is the option. And that is how, if you count the last level, how many leaf nodes will be there in the last level? 22, 32. Anyone online? How many leaf nodes will be there at the last level without counting logically? 24. 24 क्यों होगा? क्या बताया था पिछली स्लाइड में या यहाँ पे क्या लिखा हुआ है?
n factorial.
N factorial.
So where did that 24 came from? 4. Then every node get 3 child nodes, and every node get 2 child nodes, and the last we have 1 child node. That is 4. So this is a permutation tree, and we have drawn this tree in a depth first manner. You can see that the numbering is 1, 2, 3, 4, and 5. And then because I don't get a solution here, or we are checking out all the possible solutions, the next node in the data structure will be 6, 7, and then moving back parent bar, next child node 8, 9, 10, 11, 12, and so on. So this is DFS. Okay. So now I want you people to just check out the possible placings of 4 queen and tell me the solution. Take a 4x4 chessboard and try to place 4 queens and tell me किस column में queen number 1, 2, 3, and 4 is being placed, assuming that each queen is in a different row. Online people understood the question? You have to place 4 queens
Yes,
in
ma'am.
a 4x4 chessboard so that they are in non-attacking position, and tell me the positionings of the columns where 4 queens are placed, because we are assuming that each queen is in a different row. Anyone done online? कैसे किया ऑनलाइन बैठते इसीलिए मैंने को मैं 2 पे प्लेस किया 2413 Okay, fine. So this is the answer, this side that you people have got. 2, 4, 1 and 3. Is that the only answer? We'll get multiple answers. Now let us see इसके लिए tree कैसे बनाएंगे, right? So if you look over here, initially DFS follow कर रहे, right? तो हम क्या करेंगे? First queen को first row के first column पे place करेंगे. So this level is for first queen and we are placing it as at column number 1. And cells के अंदर क्या लिखा है? जैसे iterate कर रहे हैं वो numbers लिखे हुए. For the second queen, I am placing it here. तो कुछ और कर रहे थे उस time. So this is my root node wherein I need to make a decision for first queen. First queen का decision, because हम loop चला रहे हैं तो loop में directly the value chosen for the column will be 1. So this is how DFS will begin irrespective of the right part. We are moving down. तो पहली queen को place किया, अभी second queen को I cannot place in the same column, so I am placing in the second column. And there, because of my constraint, कौन सा constraint, explicit की implicit? Because the implicit constraint that relates to xi values, I get a bound here. So I'll not expand this node further. ठीक है? इसके parent पे जाएंगे, फिर क्या करेंगे? Again loop iteratively, sequentially चल रहा है. So I'll try to place the queen in the third. This is possible, so this node is generated, right? अभी मुझे डिसीजन लेना है थर्ड क्वीन के लिए, तो थर्ड लेवल पे थर्ड क्वीन की प्लेसिंग्स है. थर्ड क्वीन में 1 and 3 I cannot place because in the same column I am not placing. I'll place at column number 2. So again, because the implicit constraint, this is bound, right? Then we move to the other option that I have, that is I can place it at 4. So again, this is a diagonal conflict. So this is bound. I move back to the parent. There are no more child nodes. I move further back to the parent. I have an option of 4. Second queen को कहाँ place किया? 4 पे. Again for the next queen, one option is 2. So I place it here. For the next queen, an option is 3. After placing, I see that there is a diagonal conflict. So again, this is bound. I move back to the parent. There are no choices. I move back further to the parent. There is an option as placing it at column number 3. So again, this is a conflict. This is bound. I move back to the parent, move back to the parent, move back further to the parent. ठीक है? Manually भी जब हम कर रहे थे, all of you were trying out. तो तुम अगर सबसे पहले queen को first cell में डाला है, then you are checking out second queen को यहाँ नहीं रख सकते, next पे नहीं रख सकते, next पे रख दिया था. That is 1 and 3 were my solution. And let me draw this. Manually when I am doing, this is exactly the same. The starting से बोल रही हूँ, we are understanding the problem, we are manually solving it, then we are designing the algorithm for it, executing the algorithm and trying to assess the complexity. यहाँ इसको अगर रखा तो इस second को यहाँ नहीं रख सकते, तो we have placed it here. This is fine. For the third queen, when I am checking out, not possible here, not possible here, not possible here, not possible here, right? That is why we backtrack and place it here. Now for my third queen, I can not place it here, but I can place it here. So I'm placing it here. तो बताइएगा इस ट्री में ये पोजीशनिंग कहाँ पर है? One, 4, 3, right? Exactly, we are following the same thing. So this is bound here. Why? Because I cannot place the fourth queen over here now. हम यहाँ पे आते हैं. So this all you people know. How are we getting the solution? So first queen at 2, then second queen at 4, then third queen at 1. There are no diagonal conflicts, and the last queen at 3. So that is how you got the solution over here. Right? आगे जाके और solutions आ सकते हैं when we are expanding this flow. Is this clear to all? Online
Yes, miss.
as well? Thank you. So when you are solving it in the exam, you have to solve the entire state space tree. Depending on the marks, the question could be a single solution or multiple solutions. So multiple होंगे. तो आगे भी पूरा एक्सप्लेन. Now let us look at the algorithm. So this is what I had asked you people कि same diagonal के लिए क्या करना है, row minus column value and row plus column value, I minus j and I plus j. Sorry. So this is what is mentioned over here is, let us say two queens are at location ij and at location kl. When we are checking them for the same diagonal, so these are the equations that you can put in your code as I minus j and k minus l should not be the same. Yeah, I plus j and k plus l should not be the same for both the diagonals. So in the algorithm, we have an n queens algorithm which is calling in place algorithm. So place algorithm क्या कर रहा है? It will return a true value if the kth queen can be placed in column I. So it is checking the placing of the queen. If it is possible, then it will return the value as I. And this is again a recursive algorithm for placing n queens. I will again in the code call for n plus 1 and so on. So this is the code here. Let us look at the bottom part first. N queens, arguments are k and n. N is the size of the n queens problem and k is the queen number which is to be placed. I want to find the column for it. For wanting to find the column, I need to call whether placing the queen in ith column is feasible or not. So we'll see how place is working. अगर feasible है तो क्या करेंगे? इसकी जो वेक्टर है x wherein we are storing the values, the positioning. अभी आंसर क्या आया था? 2 4 1 3. That is being stored in the vector x. Over there for kth queen I'll place I. I क्या है? कॉलम का नाम. ऐसा करते करते if we have reached k equal to n, that means all the queens have been placed and we'll display the positionings in this particular vector. Otherwise, if we have not checked out for all the queens, I'll recursively check out for the next possible queen, that is k plus 1 till we reach till n queens. Okay, this much portion is understood. ये x of k की वैल्यू को इक्वेट कर रहे हैं एज i, मतलब हमने जब फर्स्ट क्वीन प्लेस करी थी तो x of 1 is equal to 2. 2 is the column where first queen का मतलब फर्स्ट रो एंड i का मतलब सेकंड कॉलम. फिर आगे जाके क्या आएगा? x of 2 is equal to 4. जो सॉल्यूशन है x of 3 is equal to 1 and x of 4 is equal to. Now let us look at this procedure. So what is Boolean returning is either true or false. True matlab placement is possible and false matlab placement is not possible. So this will return a Boolean value and what is happening here is इसके आर्गुमेंट में क्या पास कर रहे हैं? k का मतलब कौन सी क्वीन को प्लेस करना है. So we are checking out all the previous rows whether there is a conflict or not. So previous row में we are checking x of j मतलब कि row मतलब queen, उस क्वीन को कहाँ प्लेस किया, कहाँ पे आएगा? x of j में आएगा. x vector is storing that only. अगर x of j is equal to I, that means both are becoming in the same column. और this we are checking for the diagonal. ये कहाँ से आया? ये यहाँ से आया. And x of j minus I मतलब we have equated k को I में डालना है और j की वैल्यू कहाँ है? x of j. j is the row, x of j is the column, k is the row and I is the column. We have to identify whether we can place in column number I or not. So we are checking the same condition that we have discussed earlier. The absolute value of the difference of these two should not be same. This is fine. The same code you have to implement in the lab as experiment number 6. So for understanding, I have mentioned this over here as jth queen is at xj location and kth queen is at ith location. So यहाँ पर अभी तुम समझने की कोशिश कर रहे थे कि x of k is equal to i. So that problem that we have seen here is manually being solved. You people will write steps as per the algorithm and complete this problem as the assignment for this particular portion. Okay. Now let us move to the next problem, that is sum of subset problem. So as was explained by you people only, sum of subset का मतलब एक set दिया हुआ है, set में कुछ items है, and there is a sum such that if we pick few items from the set, their sum should be equal to n. So an example has been given. This is a set. These are the items. Sum इतना होना चाहिए, so we can pick these 3 items and we can pick these 2 items. ये manually किया. Now we'll see how the algorithm works for it. So your solution could be this type, your solution could be this type. In this case, it is not a fixed tuple. तो यहाँ पे हम क्या बता रहे हैं, वो item numbers जहाँ जिनको pick किया. So this is first, second and fourth item, third and fourth. Again, there will be concept of explicit and implicit constraints over here. The explicit constraints become your n items, 1 to n items you have to take. And implicit constraints are xi value should be less than xi plus 1 value. That is, you're picking items in the sequence so that each item occurs only once. These are the 2 bounding functions given which we are applying. Please understand this. अभी तक जितने items हो गए उनका weight का sum जितने pick कर लिए plus the next item that we are considering, we can only consider if it does not exceed m. Right. Second thing that we are considering is जितने items consider किए plus all the remaining items k plus 1 to n, you can see summation. इनका sum greater than equal to m नहीं होना चाहिए. So we'll see an example why are we putting this bounding condition as well. So please note down these 2 bounding conditions because we will use them in the tree in the next step. एक तो जितने items अभी तक consider कर लिए उनका weight plus the next item का weight should not exceed m, that is a sum, and items considered till now plus the remaining items should be greater than equal to m, then only we can expand this more. So ये 2 equations note करिए. Is it done? And people, please start taking printouts. Your submissions are all offline. Otherwise, last में rush रहेगा. You people will not. If you have printers at home, please start taking. If you want to utilize your labs, start taking printouts. जिस lab में करते हैं last में उसी. So let us see what we are doing here. So again, a constraint का xi less than xi plus 1, right? So that is why we are at the first iteration, we are selecting item 1 or item 2 or item 3 or item 4 first. अगर 1 को select किया है तो next 2, 3, 4 को करेंगे. 2 को select किया है तो 1 को नहीं कर सकते, 3 and 4 को. So that is a constraint as was mentioned here, an implicit constraint. Okay, so that is how this tree is being built. The nodes are numbered as in BFS 1, 2, 3, 4 and 5. Then 2 के बाद 6 and 7 and 8. So the possible paths are only node 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 4 and so on. Okay. So this is the first way of representing this problem. The second way could be, we'll see that later. The second way could be that we are either picking an item or not picking an item. तो इसके लिए tuple में आंसर कैसे आएगा? Instead of representing it this way 11, 13, 7 or 24, 7, we are representing it in fixed tuple. जिस item को नहीं pick किया वो 0 हो जाएगा, otherwise it is 1. So in this case, whenever at the root node, I am picking an item, the left child or the left subtree will consider item को pick किया, right subtree will consider item को नहीं pick. X1 is equal to 1, X1 is equal to 0. So this is how this tree is being built. I hope you people can understand this. At the root node for X1 item, it is picked, it is not picked. Then X2 is picked, not picked. X3 is picked, not picked. X4 is picked, not picked. This is the all possible combinations are being depicted here. Okay. So this is an example apart from the previous one that we are taking. So in this case, again, how is this to be written is I'll explain that in the next one example. यहाँ पर you people can see at the node क्या value है? 0. क्या value है? What is the node value representing? First element तो ये दे रहा है I1, I2, I3. There are 3 elements. That is why there are 3 levels. My question is कि 0, 2, 6, 12 क्या represent कर रहे हैं? Sum जो हमें लेना है. तो जब initially मेरे पास कोई items नहीं थे, the sum was 0. Now I have selected the first item, sum is 2, not selected, sum is 0. Selected the next item, sum is 6, not selected, the sum remains 2. Then 4, not selected, the sum remains 0. ऐसा करते करते whenever we have a solution that is equal to the sum that is required, we get a solution. So again, you have multiple solutions here. So again, questions asked on sum of subset can have multiple solutions. Okay. In the previous one, we did not apply any pruning because algorithm नहीं apply करें. यहाँ पे we are applying the algorithm. So let us consider the algorithm with our constraints that are written with you in your notebook. Here the value is 0. So what we are taking care of is along with this value, we are also storing the remaining cost. So initially the remaining sum is total sum. कितना आ रहा total sum? 80.
80.
Okay. So when I pick this item, now the remaining sum becomes 50. Any one of you can tell me why this node is pruned here? Because of greater than equal वाली condition या less than equal to वाली condition. So here we had a condition as summation wi ki plus weight of k plus 1 less than equal to m. That is less than equal to wali condition ki वजह से this is being pruned as well as the second condition is also satisfied. Second condition क्या बोल रही है? 12 is अभी तक का sum plus the remaining sum is 6. Sum of these two is greater than 13. That is why we need to prove this. When I move here, what is the remaining sum? Item को हमने consider किया, उसको include नहीं किया. So please remember this tree is very easy for you to draw. At each level, the remaining sum remains the same irrespective of the item being included or not. Because we have considered that item, but we have not included that. So here it will be okay. So we were able to fill this. Why is this being bounded? Because of less than equal to constraint 7 plus 6, 7 plus 0. Do I have any items with me? Any items left with me? They are not left. So there is no sense of expanding this node further. वो जो loop था हमारा items था वो loop finish हो गया. What about this? Why is this being bounded here? Sum is greater than 10. Here. Is an equal to condition. Both item has weight as 6. I could have drawn the left child 9 कर सकते थे ना 9,0 इसका लेफ्ट चाइल्ड कर सकते थे कि नहीं 9,0 by including the fourth item. I'm talking about this. Is this possible? Yes or no? And now these are proved. ठीक है? इसको क्यों प्रूव किया? Which condition? हम greater than equal to. इसको क्यों प्रूव किया? Right? And then these are proved. Then what about this? यहाँ पे we need to draw कितनी वैल्यू आएगी 9,6 here next this and proving them further because there is no solution. How many solutions have we got? One solution, and this is solution path over here. So we are including all the items or not? Solution क्या है in the form of four size का tuple? Binary vector क्या बनेगा?
1101.
So this is how we'll be solving the state space search tree using depth first search, and you will again mention why the इसके लिए क्या कर सकते हो wherever you are bounding you can mention because of first constraint or because of the second constraint or because the loop has finished you can mention 1 2 3 as a number so that the tree is neat and clean. And definitely, again, please do not miss on mentioning the equations. That is important. So this is the algorithm that we were following. क्या कर रहे थे? Sum of subset S, K and R. मैंने वहाँ पे 2 ही arguments लिखे, but you people can follow 3 argument method as it is in the next slide. 3 arguments का मतलब पहला जो है वो sum बता रहा है, दूसरा remaining sum बता रहा है, the last one, and this one is which item we are considering. For the next slide, ठीक है? तो जो चीज यहाँ पर लिखनी पड़ रही थी I1, I2, I3, so we are itself writing it over here as a 3 vector data. If including the item we are getting a value as equal to m, इसके लिए पिछले वाले स्लाइड में बाउंड किया हुआ था right here and not expanded here. Why? Because less than m accepted नहीं है. You're getting my point here. If I include this is 3, then if I include this becomes 9. Left child जो मैंने draw किया था 9 बन रहा था, right? But that will be less than m. And we have considered all the 4 items. So again, that is not accepted. That is why this is bounded here. So again, that thing I wanted to explain you through the code. That is why उधर मैंने manually solve किया. If S plus WK is equal to M, then we are displaying. Otherwise, not. Else, if inclusion of the next item is not exceeding the total sum, then I am iteratively calling this again with what arguments? S की जगह अभी S plus WK हो गया sum. K item की जगह K plus 1. Next item will consider, and जो remaining weight था अभी कम हो गया by WK. So this is for the left child. For the right child, what we are considering the data is both the values, that is S plus WK less than equal to M and S plus R minus WK greater than equal to M. These both bounding conditions are being checked, and we are not including this item and following sum of subset with ये item नहीं include हुआ, इसके लिए S ही रहा, K plus 1 because we have to check for next item, and remaining weight, the thing that you people were doing wrong, मैंने उस आइटम को लिया नहीं है, बट कंसीडर किया है, इसमें रिमेनिंग वेट रिड्यूस हो जाएगा बाय WK irrespective of the item being included. So what should be the initial call to this sum of subsets? रूट पे ये 3 आर्ग्यूमेंट्स क्या रहेंगे?
Sum, item and remaining.
Remaining items. So what should be the remaining items? That is summation Wi, which is given to you. 0, 0 and summation W. जिससे कि मुझे क्या पता चलेगा? First level पे the second argument will be 1, second level पे the second argument will be 2, and so on. So initial call is sum of subset 0, 0 and summation of Wi. Okay. So again, I have tried to draw this, लेकिन अभी भी incomplete है, so you have to complete this. Let us discuss what is happening here. हमारे पास ये डेटा दिया हुआ है. Total sum is 30 and there are 6 items. तो जैसा मैंने बोला 3 values होनी चाहिए. Initial sum, which item you are considering at that particular level, and what is the remaining sum. So the remaining sum is 73. I am considering item number 1 at the next level, and this is 0. Considering the item, not considering the item, so this is first item का weight add हो गया 5, इधर add नहीं हुआ, and दोनों जगह reduce हुआ by the weight. Similarly, at the next level, and next level. Reason for this bounding. Less than equal to वाला condition भी greater than equal to वाला condition is being followed. Greater than equal to. सम इधर कितना आ रहा है? 73. So we are still at. ये condition बोल रही थी greater than equal to, so that condition is also satisfied, और दूसरी condition भी हो रही थी कि नहीं हो रही थी? is less than equal to m being satisfied. Add this child node जहां पर include करेंगे next item को 27 plus how much 13, that is 40, that is exceeding 30 na? So both the conditions are being satisfied. So you have to mention that condition number 1 and number 2 is being satisfied. That is with by this is being published. What happens here? Less than equal to condition satisfied nahi hogi. We are exceeding 30, but second condition is being satisfied, so you are not mentioning the second one here. So likewise, again you can see there are multiple solutions being given here. Though the tree is not being solved fully completely. यहाँ पर मुझे right भी draw करना है, यहाँ पर left भी draw करना है, but because of lack of space, जहाँ solution आ रहे थे वो path have been shown to you. And for example, for explaining purposes, I have written bound over here because these are not solved further. Okay. So what you do in exam is, as initially also I was telling people, notebook को landscape में रख के you can draw the left subtree in one page and the right subtree in another page. In exam, definitely you will not get 6 weights ka question. It will be 4 weights, but still, if you cannot manage space for readability purpose, you can split the left subtree and right subtree on different pages. Okay? Any problem? Any questions on this? Yes, attention immediate addition. नहीं बाउंडिंग खाली बतानी, हर इटरेशन पे क्यों बतानी? यहाँ पे तो डायरेक्टली आ रहा है ना. This is sum and this is minus. जहाँ जहाँ बाउंड होगा that you have to show. जहाँ पे वैल्यू बाउंड हो रही है, you have to mention whether it is through equation 1 or through equation 2, or because of this condition. Okay. Again, this is for practice purpose. You have to solve this as per the instructions that is given to you. So we take a break over here before we begin with next two problems. So why is this an optimization problem? क्या हुआ, सुना नहीं ना? Why is graph coloring an optimization problem? Because we have to find the minimum number of colors so that we can color the map or the graph such that no two adjacent vertices are the same color. That is a term that is being used for minimum number of colors as chromatic number, the smallest number of colors used to color the graph. And there is also a 4 color theorem which क्या बोलती है, any map on a plane can be colored with no more than 4 colors. We do not require more than 4 colors. जितना भी बड़ा map हो, a planar map or a planar graph, so that no two countries with a common border are of the same color. So where does this problem originate from? This is a graph given, and in this graph, agar question is whether the graph can be colored or not. So that becomes a decision problem. कर सकते हैं कि नहीं कर सकते? When I need to find the minimum number of colors to color the graph, that becomes a optimization problem. Or we are calling it as a chromatic problem also, because chromatic number is minimum number of colors required to color the graph. Again, this can have more than one solution. We will see an example where we have multiple solutions for coloring the graph. This is just random coloring without considering minimum number of colors, or without considering that इसको और इसको तो हम same color रख सकते थे, right? So this is an example of map coloring, and accordingly, this is an example where more than 4 colors are not being used for the same graph, and here more than 4 colors have been used. Right? So how does the algorithm work for map coloring? Is we have a number of vertices, we have a number of colors, so we label them. We start assigning each color to each vertex, While assigning the colors, again we make sure that connecting vertices का same color नहीं होना चाहिए and minimum number of colors should be used. So why should the complexity be n to the power n in this case? Anyone online why the complexity should be n to the power n? So graph coloring. Please consider कि हम backtracking पढ़ रहे हैं और backtracking में the base is a tree. So in that case, at the very first node, I have how many choices? For the first vertex, n choices. And for the second vertex, again, there will be so many choices, right? And then we will pose a bound through the constraint. So this is an example. Again, half I have drawn. You can complete this example. Let us understand. छोटा सा graph लिया गया है, wherein there are vertices as 1, 2, 3, 4. I have to color this graph. So what do I do is again tree based जो भी problems रहेंगी for backtracking and branching out, each level we are considering for each instance. तो यहाँ पे instances क्या है vertices. So first level is coloring vertex number 1, second level is coloring vertex number 2 and so on. Vertex number 1 को color करने के लिए the possibilities are R, G and D. These two child nodes have not been drawn. अगर vertex 1 को R color किया है, so again for vertex 2 the possibilities are R, G, D. Wherein this possibility is ruled out because of the constraint. You are mentioning that and then you are bounding that. So I move here. I again check whether I can place for the third vertex I can place an R or not. I can, because third is not connected to 1, right? And for the fourth vertex, can I place an R? I cannot. Can I place a G? I can place because again 2 and 4 are not connected. So ये feasible solution होगी. So likewise, you will complete the tree and you can see there are so many feasible solutions in the first half subtree only. There might be others in the second half subtree as well. That is why graph coloring can have multiple solutions. Only constraint is it should not use more than 4 colors. It should use minimum number of colors. 4 vertices है तो we are done with 3 colors. We could have colored this with 4 different colors as well, but we have to choose minimum number of colors. Okay. So graph coloring is as simple as that. You might be given a graph and you may be asked to draw the tree and find out the possible configurations where the constraints are met. कौन से constraints? 2 vertices should be having the same color and minimum number of colors should be used to color the graph or not. These are the various applications of graph theory. Can be used in computer network security, timetabling problems, GSM mobile networks. It can represent natural language passing diagrams. It can be applied to pattern recognition and molecules in chemistry. So that was all about backtracking. We saw what the problem is. How are we solving them using DFS, right? Now moving to branch and bound. So again, नाम ही बोल रहा है कि we have to branch at each node and we need to try to bound that a particular node if a particular condition is there, so that the search space tree is proved. So branch and bound is used again to find optimal solutions to optimization problems. It is applied when greedy and dynamic both fail. This is slower and again requires exponential time because we are using a tree. It will use a state space tree wherein all the children of the node generated before expanding any child, because we are following BFS, right? So let us differentiate between the two before beginning to learn branch and bound. Backtracking follows DFS, branch and bound might follow DFS, BFS, and best first search as well. Do you people remember best first search covered in IIS? There was breadth first search, there was depth first search, and there was best first search in IIS. That was there in the syllabus. Best first search is I am computing a cost for each node, and according to that, जरूरी नहीं है कि मैं ऐसे move करूँ या ऐसे move करूँ. According to the cost, I can switch to a node which is having lesser cost. So even if I am moving depth first manner, I can backtrack to a node which is than the previous level having lesser cost. That we have used best first search and 15% problem in IIS. Backtracking solves decision problems, branch and bound solves optimization problems. We in backtracking, while finding the solution, we might make a bad choice. Over here, the possibility of bad choice is ruled out. We search the state space tree until the solution is found in backtracking. And this is searched completely since the solution can be found elsewhere because we are moving in breadth first search manner. Space requirement for backtracking is we go of height of tree. Over here, it is we go of number of leaves in the last. So the applications are 15% and traveling salesman problem, of which in syllabus we have only 15%. So again, there are few terminologies related to branch and bound. एक state space tree बना रहे हैं. All the children of E node, that is a live node, that is the node जिसके children are being generated right now. So all the children are generated before any other node can become live node because we are following BFS. For exploring new nodes, these are the implementation strategies. I can either use BFS using PicoQ. I can either use research using LIFO stack, or I can replace PicoQ with priority queue. Then this becomes least cost search. And we call that as best first search as well, because priority में हम वो nodes को डालते हैं पहले जिनकी cost कम. Or we call that as a heuristic value, or we call that as a function that is computing the value. The search for an answer node can often be speeded up using an intelligent ranking function. यही ranking function हर node की cost बताता है. For the live nodes, though it requires additional computational effort. तो cost निकाल रहे हैं तो definitely कुछ time लगेगा cost compute करने में. In this method, a space tree of possible solutions is generated. Partitioning is done at each node, and we compute lower bound and upper bound. Whenever lower bound exceeds upper bound, we prune that particular node, and this process is called as patterning. We might again be asked these terminologies in Viva as well related to backtracking and branch and bound. So what do we understand from this is branch and bound क्या करता है? Value compute करता है, that is a bound, and that decides whether the node is promising for it to expand further or it is not promising to prune that particular node. So this approach is called as best first search with branch and bound. If we are not using this function, जो function पिछली slide में बताया, if I am not using this intelligent ranking function, then this becomes a breadth first search with branch and bound pruning. We are only moving level by level. It is not being implemented using priority queue. It is normally implemented using queue or stack. So this is the algorithm that says a E node, that is the node which is being expanded, till the time it has child nodes. If he is a final leaf node, I'll write the solution because I have moved to the leaf node. If it is not, I'll expand this node. Where am I storing all these nodes? We are storing in a heap. That is a priority queue. As per that, we'll delete the top node which is having least priority, which is having most priority or least cost that I choose from the heap. So this expand algorithm क्या कर रहा है? It is generating all the child nodes. It is computing the cost of each child node, and depending on that, it is inserting each child into the heap. और heap में से कौन सा child node pick up करेंगे? जिसकी cost सबसे कम है या जिसकी priority सबसे ज़्यादा है. So this is how we are implementing least cost search using best first search technique. So this is my intelligent ranking function. ये तो पढ़ा होगा in IS. The heuristic function fx, gx, hx, is intelligent systems में I have taught intelligent systems many times. You can take it, but it is not covered. So I'll tell you over here. तो ये clause क्या बोल रही है? मुझे root node से करंट नोड पे आने की कॉस्ट पता है क्योंकि मैं ट्रैवल करके आई, बट आई डू नॉट नो फ्रॉम दिस नोड टू माय गोल नोड व्हाट वुड बी द कॉस्ट. That is an expected cost. That is why you can see at G a cap is there. That is expected cost, and that is why the total cost also becomes an expected cost. Okay, an estimate. So this intelligent ranking function is an estimate of the additional effort required to reach an answer node. I have not reached the answer node, but I have traversed from the root to some intermediate node. Okay. So the branch and bound guarantees you termination for finite space trees. That it will guarantee you the solution or the optimal one. As I mentioned, we'll be covering 8 puzzle problem. 8 puzzle problem you must have covered. 8 puzzle. Yes, possibly kaise? This is a very basic problem that we study in IS. Anyone online? I am drawing over your 15% problem. अभी याद आ रहा है? अच्छा, so sorry. I think IS तुम लोग का सेम 5 में. So sorry, my bad. तो ये क्या है? ये 15 puzzle. यहाँ पर there are some numbers and there is a blank tile. That is a puzzle wherein I have to move this tile and bring it in this formulation. कोई और formulation भी दिया हो सकता है. So this is a positioning for 8 puzzle. तो मुझे ये haphazard manner में दिया हो सकता है. I have to bring it in sorted manner. ठीक है, फाइनल सॉल्यूशन क्या होगा? 1 2 3 4 5 6 7 8 ऐसा प्राप्त है. So this is 8 puzzle or 15 puzzle problem. Something like this. The initial state 8 puzzle is given to you. You have to reach the final state. तो हम मैनुअली कैसे सॉल्व करेंगे? Anyone of you can try. ये ब्लैंक टाइल को अगर वहां पर है इनिशियल स्टेट में तो आई कैन आइदर मूव अप, डाउन और लेफ्ट. अगर सेंटर में होती तो आई हैव 4 पॉसिबिलिटीज टू मूव टू 4 चाइल्ड नोड्स विल बी क्रिएटेड. अभी यहाँ पर है तो हाउ मेनी चाइल्ड नोड्स विल बी क्रिएटेड? 3. अगर कॉर्नर पे है तो देयर आर ओनली 2 चाइल्ड नोड्स व्हिच नीड टू बी क्रिएटेड, राइट? So likewise now you can imagine we are trying to reach to the goal state and how huge the search space tree will become. The same problem we have to solve using branch and bound, so we compute the cost. अभी cost क्या निकाल सकते हैं? So there is a heuristic value that is computed. Heuristic का मतलब होता है I am giving some more information to the algorithm for it to move in good direction. यहाँ पे heuristic क्या हो सकती है? Number of misplaced tiles. So can you people count number of misplaced tiles from initial state to final state? So the count value is 3. ऐसी वैल्यू माइट चेंज इफ अ डिफरेंट इनिशियल स्टेट इज गिवन टू यू. ये 15% प्रॉब्लम है तो वैल्यू बड़ी भी हो सकती है. तो मेरा ऑब्जेक्टिव क्या होना चाहिए कि इस अगर अभी 3 वैल्यू आ रही है, फाइनल स्टेट की ह्यूरिस्टिक वैल्यू कितनी होगी? सेम टू सेम इज 0. सो वी आवर ऑब्जेक्टिव इज टू रिड्यूस डाउन दिस ह्यूरिस्टिक वैल्यू. ऐसा पॉसिबल है कि आई माइट टेक अ पाथ वेयर दिस ह्यूरिस्टिक वैल्यू इज इंक्रीजिंग. आई एम मूविंग अवे फ्रॉम द गोल स्टेट. That is how LC search makes you move to the globally optimum solution. So this is a solution for this. मैंने क्या बोला था? अगर यहाँ पर टाइल है तो there are 3 possibilities. So this is being moved down here, being left here, and moved up here. Cost compute कर रहे हैं हर नोड. Cost क्या होगी? अभी इंटेलिजेंट रैंकिंग फंक्शन क्या बोला था? जितना मूवमेंट हो रहा है, जितना काम मैंने किया प्लस जितना काम मुझे करना है. So I do not know how much work I have to do. That is being computed using the heuristic function, that is the estimate. So the second value after the plus is your heuristic value. As you can see, here the heuristic value changes to 4. How? इसको अगर इससे compare करेंगे तो number of misplaced tiles is 4. Why am I adding this 1 here? One is the work that I have done till now. So this equation was fx is equal to gx, cx is equal to fx plus gx, and fx is the cost of reaching x from root. I am currently at x, इसकी मैं cost निकाल रही हूँ. Root से x तक अभी जो movement लिया उसकी cost कितनी है? A single step. That is why I have chosen this as 1 here, here and here. आगे जब choose करेंगे तो again 2 levels cross किए हैं तो cost is 2, 2 and 2, 3, 3 and 3. Right? Among these nodes, which node should I traverse? The one with minimum cost, because heap जो मुझे return करेगी, so this is max priority min cost node. That is how LC search works. So when I'm expanding this further, now you people think and tell me, ये 4 child nodes क्यों नहीं बनाएंगे? So if there might be a child node that is same as a parent, so you will get stuck in a loop. So when you are implementing, again this you have to implement in branch and bound, that is experiment 7. You have to ensure that a child node need not be generated same as a parent, or parent need not be generated as a child. That is why 4 की जगह 3 child nodes are there. We are not moving right, we are not moving right, we are only moving up, down and left. Again over here, there should have been 3 child nodes, but only 2 child nodes is generated. And last May, when you get the intelligent ranking function value as 3, that is the same as initial node, that is 3 levels we are traversing, the cost of reaching is 0 because we have reached to the goal. So this is where we will stop. So again in exam, you could be given a different configuration of initial state. You have to follow these steps using branch and bound. Is this understood? So this is a configuration given to you for assignment. Again, for this chapter, you have 4 questions that are required to be solved. Again, the deadline I'll keep as Sunday night. FA will be combined for module 5 and module 6 at the end, and that will be covered as your ISA 3 iske marks out of 20, and then best of 2 ka average is being taken. ISA 3 is up to the faculty how it takes. It will not be conducted at the institute level. So faculty to faculty, जो जिसको जैसा करना है वैसा करना. But we were not getting any turns for that purpose, so we took it that way. अलग-अलग faculty. Okay, so that was all about module 5. Any questions online?
No, ma'am.
Any questions offline? Offline वाले तो खुशी मना रहे हैं. टेस्ट की खुशी मनाने लगे.
No, ma'am.
नहीं, इधर offline. Okay, then I'm done from my side.